and take pictures or whatever notes that you need to do of the screen, or download the PowerPoint and follow along with me. Give me 1 sec to turn this fan off. All right, so we've sort of talked about acids and bases before, but we really are going to talk about them now. So some definitions. There are multiple ways that chemistry they describe acids and bases. The most typical one is called an Arrhenius definition. We've never really talked about it this way, like saying, oh, hey, the Arrhenius definition is this, but from now on, just know that an Arrhenius definition of an acid is something that when it dissolves, it increases. I should bracket, or you'll think it's concentration in parentheses. It increases the concentration of hydrogen ions. That's all an acid is. So we've been using HCl all trimester, all year, as an acid, hydrochloric acid. And that's because when you put it in water, it dissociates to H plus Cl minus. So we have this thing of water. Water has its own amount of H plus already, some OH minus, but mostly HOH together. And then I add an acid, which is HCl. It breaks apart. It increases the concentration of that. So an acid is something that increases the concentration of H plus. All right, so thank you. Got a little hot there. Okay, now a base increases the concentration of hydroxide ions. Tell the people next to you a common base we've been using all trimester. I heard Tolman say it. Say it louder, Tolman. Sodium hydroxide. This is a strong electrolyte or a strong base, which means it completely dissociates in water. So if it completely dissociates in water, it's really Na plus, which we learned in 4th chapter that we don't care about, and OH minus. So since the concentration of hydroxide increases when I add NaOH, we call it a base. That's the Arrhenius definition of an acid and a base.
What is Arrhenius?
It's the last name of the scientist that made that definition.
Oh, like just made acids and bases, like what acids?
Uh-huh. That is serious.
All strong bases are strong electrolytes. Is that just anyone?
No, every strong base is a strong electrolyte, but not every base is a strong base. So not every base is an electrolyte. So if I put, barium hydroxide, it only dissociates a little bit. It's still a base because it causes a little rise in OH minus, but not very much. So we call it a weak base. So far, so okay. All right. That's a lot of stuff. All right. Bronsted-Lowry is slightly different. They both pretty much have the same idea, but a Bronstead-Lowry, and that's the names of 2 people that came up with this, they define an acid as something that donates a proton. Anyone know the formula of a proton? H plus. So really, this one's not much different. So if I have HCl, it dissociates to H plus Cl minus. It's a proton donor. You okay with that? All right. So the Bronsted-Lowry acid is pretty much the same, but a Bronsted-Lowry base is not always exactly how the other one looks. And this is why NH3 is a base. Would NH3 be considered an Arrhenius base? Yes. It's kind of dumb. No.
Because
I'll show you. Go ahead. Hold, Grace. Yes. Say that again.
when it dissolves in water, would it bond with one of the oxygen molecules?
No. Close.
With one of the H's?
It takes an H plus from water and it takes one. So that would mean the amount of OH minus goes up. So it's kind of tricky. Go ahead. But typically, we would say NH3 is a Bronsted-Lowry base because it accepts a proton.
So when NH3 is put in water, it makes ammonium,
Uh-huh.
and that's how it gets. So it goes
Right.
from NH3 to NH4, does it?
Right.
Does that make a solid, or is it,
No.
is it aqueous?
It's aqueous. By bonding with an H plus, it causes the H plus to go down. Now think about Le Chatelier's principle. If we take away here, this will fight that by forming more of this. So if NH3 causes this to go down, it's also causing that to go up. So it doesn't look like a standard base with an OH minus, but it works. It works. Here's another base that you wouldn't think about, but it's Na2CO3.
If Le Chatelier's principle is always trying to do the opposite of what we're adding,
Okay.
how do reactions happen? Is it just
Well, it still has to reach equilibrium in the first place. And so that's just Mother Nature going whichever way is favored. But then our opposition to it happens once we adjust the equilibrium. So nature takes care of equilibrium. We mess it, and then nature tries to fix what we mess with.
okay? So Chatelier's principle is really about after the
After it's at equilibrium, yes. Go ahead.
Wait, so this one's different. Would it like separate to make CO2 and then the extra O would then take both, would take one of the hydrogens from it?
Kind of. Sort of. Yep, you're both there. So if I add this to water, it makes Na plus CO3 minus. And this is happening. So both of you said it, just not the whole thing. This is happening in water, which is HOH, but has some H plus and OH minus. We okay with that? All right. This goes in. This is a spectator. We don't really care about that. So CO3, and we learned this before. CO3, it grabs H's to make H2CO3. So it will become H2CO3. But this is the part we've learned before. Does this stay that way very long? No, it doesn't like to be that way. So pretty quickly, it breaks down into H2O plus CO2, which if we combine both of what they said, then you'd have the right answer. So what this does, it accepts protons. If I decrease the concentration of H plus, then I have a base. Now, typically, just putting this in plain water, you don't see a whole lot of any change. But if I put this in an acid, which has any excess H plus, then this really, really happens. And you've seen this before. This is vinegar plus baking soda. We are neutralizing the vinegar by adding a Bronsted-Lowry base. And we can neutralize it by adding an Arrhenius, just pouring in sodium hydroxide. But this is a more fun, bubbly way to make that work. You all right with that so far? So you got to be careful where these can creep up. But usually an acid will start with an H, a base will end with an OH, but there are some that are tricky in our Bronsted-Lowry base.
Are most of them fixes that are different?
Because a proton donor has to have an H plus, because that's what a proton is. But the thing that accepts a proton, there can be any negative thing that can take a positive. That would be cool. All right, so this is basically what we just said. A Bronsted-Lowry acid must have a removable proton. A Lowry base must have a pair of non-bonding electrons. This is a whole nother way to look at it. So these non-bonding electrons are slightly negative. They can attract the positive from hydronium. Because H doesn't want to be H plus. It wants 2 electrons, really. So if NH3 was here just chilling, and NH3 was happy, it was fine. But if there's a plus sign right there, why would this proton not attract to those? Well, it does. But then it's out of charge, like out of balance. So we end up with this being a polyatomic ion called ammonium. So that's tricky, but it's doable. I'm sure you've already read these, right? Or you will. Okay, if it can be either, this is a word you should know. We call it amphiprotic. So that means it can accept or it can donate. And these will make sense if we write them out. We have hydrogen carbonate. Hydrogen carbonate is not how it naturally is found. It's found as carbonic acid, which is H2CO3. In order for this to become that, what did it do? Gained what? Gained a proton. All right, but we also know about the carbonate ion. What's the carbonate ion? CO3 minus 2. So how did this become that? It lost a proton. So if I have HCO3, I can put it in water and have it behave both ways. Yes?
So then are those molecules like the ACID? Are they gonna be
Yeah, fairly, because they'll do either one. They're great for what we call buffers. Buffer, and that's when this class gets hard. So we do the math with buffers. Buffers are things that can do either one. They can absorb or they can give off. And that's why we have them in our blood. You've heard of the carbonate, hydrogen carbonate, whatever it's called, cycle. Have you not? Do you learn that in AP Bio? Okay. It's the carbonate, hydrogen carbonate, something. Let me look it up. Well, it might just be called carbonate, but it is both of those. Let me look real fast.
Wait, how can you gain protons?
You just have to be something that's negatively charged and it will attract one. That's tricky. Whoops. It's 3,9. or if you feel like it, reducing it to 1/3.
No, you could have reduced
I-
every number by 3.
I know. Here we go. The bicarbonate buffer system. I felt like I was talking, but maybe I wasn't. John, I yield the floor to you. Cooper, I yield the floor to you. Okay, thank you. So it says the bicarbonate buffer system is an acid-base homeostatic mechanism involving the balance of carbonic acid and bicarbonate ion and carbon dioxide in order to maintain the pH in the blood and duodenum, among other tissues, to support proper metabolics, function. Catalyzed by carbonic anhydrase, carbon dioxide reacts with water to form carbonic acid, which in turn rapidly dissociates to form bicarbonate ion and a hydrogen ion, and is shown in the following reaction, yada, yada. As with any buffer system, the pH is balanced by the presence of both a weak acid, the H2CO3, and its conjugate base, which we'll learn about in a second, HCl3-, so that any excess acid introduced to the system is neutralized, and any excess base would also be. All right, failure of this system to function properly results in acid-base imbalance, such as acidemia and alkalemia. I've never actually heard of that in the blood. So your blood needs to be at a very specific pH. Oh, that was not on the screen. I'm sorry. Wants to be there. I thought that was on the screen. I forgot I turned that on. So look right here. We have something that can attract the H. We have something that can attract the OH. So in our own blood, we produce a system to offset changes in pH. It's called a buffer, and they're super, super important. Without them, we would not function. And we'll learn about that. That's where chapter 16 and 17 are going. But a buffer can go both directions. It's pretty miraculous. The body is an amazing machine. And to me, it's amazing it doesn't break down more often. Like so many things every day have to go right. And for most of us, our whole life, knock on wood, they do. And then you just get old. And yeah. Yep. Okay. This is an extremely important concept. So make sure that you're okay with this. This is really, really, really important. And that would be the idea of conjugate acids and bases. All right. Conjugate comes from the Latin word conjugare, meaning to join together. All right. Reactions between acids and bases always yield their conjugate bases and acids. Okay. So it's not that bad. We look at it the following way. If we have an acid and we react it with a base or water, that's not bueno. I just got a text about my quarantine information.
Are you quarantined?
Who? I don't know. No.
Me? Yeah, I guess why would you joke about that? Garrett? Are you quarantined? You can't say this.
Oh my.
Okay, so now I give you permission to tell.
Yeah. If all I get is that text, I'm not. Oh, I got an email.
Hey, you need to walk out of this classroom right now.
Nope. I did that one day. Was that this hour?
I don't think so.
It was very dramatic. Like,
What if you have COVID?
I don't. Okay, we'll be fine. I'm right here. Okay, look. So, an acid is something that loses an H plus. A conjugate base is something that would gain an H plus in the reverse reaction. Or it's the acids anion. Because what does a base do? A base accepts a proton, right? If we reverse this reaction, what does NO2- do? It reacts, it gains an H plus to become HNO2. This is the reverse reaction. Okay. So the conjugate base is always what lost the H. The base, H2O in this case, it gained an H plus. So the conjugate acid is the thing that in the reverse reaction will lose. They do actually make sense. It just takes some practice to get used to them. Just a bad habit I have. All right.
Wait, really quick.
Yes. Is it?
They're all saying it is.
I don't know. He wasn't at lunch today.
Oh, really?
Yeah.
Speaking of birthdays, my birthday is in fact 2 weeks.
Okay.
So I will be expecting honorary free happy birthdays for the next 2 weeks.
Okay. I go first. Fabia. Happy birthday, my friend. All right. So here's what happens when an acid dissolves in water. Water acts as the base. That means it takes or abstracts a proton from the acid, and that becomes H3O. I'll just undo all this because it was cute. There can be, but usually no. But we're going to actually write it that way. Yes.
Okay, so H plus is a proton.
Yep. So H plus, good question. I should have said this forever ago. If I draw the hydrogen atom, just one of them, it has a proton in the middle and an electron. H plus would mean it lost its electron. So really all it has is its proton. I really should have done that forever ago. Thank you for asking that. I'm so confused. It says, Tom, your test results sent to the Department of Health. I haven't tested for COVID in months.
Wait, are you positive?
I wasn't even there.
Someone is positive then.
So who was testing for you?
That's a great question. I cannot
You didn't test this
answer.
morning, did you?
I did not. Just like that. Sorry, that's why I say it's a bad habit, because now you won't pay attention. Oh, that one wasn't cool. Okay, ready? So here we go. Water accepted a proton to become H3O. Fair enough? All right, now, as a result, the conjugate base of the acid and a hydronium ion are formed. So this HCl donated its proton. So now we have Cl minus. If we reverse the reaction and look at the conjugates, Cl minus, the other direction, would accept it. That's why we'd say Cl minus is the conjugate base, because in reverse, it would accept the H plus, and that's what bases do. Then in the reverse, H3O would give away its H plus, and that's what acids do. So we would say it is the conjugate. So whenever we talk about the acid base and the conjugate acid and base, you flip it and then just apply the same rules. Is it accepting or donating? All right. I know it's tricky. Read the book and practice them. These, I think the next slide's a bunch of practice.
So it can go either way. Like with the reverse reaction,
Right.
there's always going to be a conjugate.
Uh-huh. Okay, I lied. Well, here was one. And we'll just write it out. So I'll do a different one. About HNO3, and it's dissolving in water, or whoops, we are reacting it with water. And it's going to make, the H is going to leave and come to the water. It makes H3O plus. plus what is left over? NO3 minus. Would you label the acid the base, the conjugate base, and the conjugate acid? I think I know what's wrong. My children tested, and I just wrote my phone number down as them. Neither one of them tested positive. Kind of. I don't know. No, neither one of them tested positive. I would have known early. We knew by 9 that only one person tested. Can't tell you. No. I'm not, probably.
He didn't test positive. So we're supposed to do acid base, conjugate base, and conjugate acid, not this.
That's it.
I think I did it. Which means it's been 2 days.
All right.
Oh my gosh, David said I did it.
Here we go. Here we go. All right. Which one is the acid? All right. This is the acid. Then that means this is the base. Okay. On the other side, who donates H plus? Donates H plus. H3O, which means it is the
Acid, right.
conjugate acid. And this would be which one accepts the H? All right. All right. Okay. No, definitely not. All right. So it's not.
I'm asking for a replacement.
It's not awful. Oh, that's not what I want. Here we go. This is what I'm asking for, the same thing on these 3 problems. I'm looking for the acid, the base, the conjugate base, the conjugate acid. Ready, go. Yep. Are you done, Cooper?
Yeah, I'm done.
Oh, looks like you're not. I'm gonna punch him.
It was trying.
That was a little hurtful, Reese. But I liked it.
Oh, I just reminded that I was laughing so hard that I put my head down.
All right, you want to come up and write one, Fabian?
Okay, let's see if I can do this. Oh, can I write one?
I have a lot of confidence.
No, Fabian actually did it.
Vitamin the butt later on.
All right, here we go. We will judge him literally. Do we agree that that's the acid? Wait, it doesn't start with an H though. It's okay. Okay, good. Who agrees? ABCACB. I agree as well. All right. Yes.
Can you explain why the first one is not a base since it has an OH and water?
Let me rewrite this. It is H C2H3O2. It's called acetate or acetic, sorry. Acid. Yep, this is vinegar. I'll answer. Let me finish, and I certainly will give you the answer. This is called its structural formula. This is called its chemical formula. When you get into organic chemistry, they will draw this out so that you know it looks like this. And then you're like, well, wait a minute, there is an OH, but there isn't. There's an H stuck to this piece, and it's tricky. I'm certainly aware of that, but we can look at this. If you want to rearrange it, put everything together, start it with an H, and then you'll see it is pretty clear that that is vinegar. I don't know. Yeah, you can look at that and notice that, hey, this H was abstracted, so it was removed. So that would be the other way. Who wants to do number 2 for us? All right, John. Just draw with your finger.
This is the acid.
HCl is an acid, we concur. Okay.
How is it not?
How is this not an acid?
Concur.
Yeah, is it concur? Is it I concur? And then
Concur.
because it is all in concur.
Cooper, why are you laughing about that?
I like that word. I concur.
I've never heard Cooper.
All right, well, you two shut the freak up. What is the beef between you guys the last 3 weeks? It's so annoying. All right, anyone agree or disagree? Sorry, anyone disagree with number 2? All right, we agree. This is the acid. If we reverse the reaction and went this way, all right, this one accepts the H plus, so that means it's a base, which means this is the acid, because this way it would give off the H plus. All right, who wants to do number 3? All right, Bennett.
It's so hostile.
BACBCA, who concurs? Who can concur? This kid. All right, do we feel okay about these? There's a ton of them in the book. You can practice. You can go on the internet and find conjugate acid-base practice and practice them like crazy. All right. Yes.
Four just was. Sorry.
Was 4 on the screen before? Okay, try it for a minute. Everybody try it for a minute. See what I mean, Nisha? It's just a bad habit. It keeps me entertained. It's not a bad habit. It is when I kick it and someone gets hurt. Because I have this, but it doesn't work very often. See? Okay, anyone have number 4 done? All right, Tolman, you raise your hand. You want to try it? This screen emits UV, so there's no COVID on it. That was a joke. Yes. All right, who agrees? Me too.
Couldn't you just look at the right-hand side if you're wondering what it is? Because NH3 is a base.
Yeah,
And you
it's
just put conjugate.
that's absolutely fine. No. NH3 will always be a base because it accepts a hydrogen to become NH4. So we know this is an acid because it lost an H or donated a proton, right? We know this is a base because it accepted the H. We know this is an acid because it lost going that way. We know this is a base because it gained going that way. This one's actually sort of easy. Like there's no H here, so that's your base. Right there, you got those pretty fast. We okay with that? All right, then, well, we know this to this, it lost, so that must be my A, this must be my B, and on the right side we put C's. You can get them pretty fast once you get used to them. Okay, what time are we out of here? Okay, we'll probably make this the last subject. All right, acids and base strength. Strong acids are completely dissociated in water. Oh, make sure you understand this part. Their conjugate bases have negligible basicity, meaning they resist protonation. Protonation. It means that they don't take one. Cl minus does not grab H and come back to HCl. So if we were going to say it had a K value, it'd be a really small one. Hardly any products in all, or sorry, the other way around, really large one. It'd have almost all products, the HCl. I'm confusing myself. So I'll show you, it's in this picture. Hold on, go ahead. It's just showing you its conjugate base. Right here.
Why is that less basic, or why is that less basic than water?
I'm not following you. I'm sorry. Maybe Fabian can answer because I don't understand your question.
Isn't it because like the water molecules will switch between OH and will have a like concentration of both OH and just H plus?
They do have both.
Fluctuates.
It does fluctuate at equilibrium.
It would have a different effect compared to different bases because like well, the more neutrality it is, because the less effect it would have on the constant fluidity of how much water separates between OH and H plus in water.
Did that answer your question? Because I'm confused. Yep. Thanks. Leave it to Reese. We'll figure out. You ask me face to face, and I'll see if I can figure out. Okay. What I'm trying to say here is when I have HCl and it decomposes, I keep saying that, when it dissociates, the concentration of H plus will be really high. Almost 100% of it breaks apart. Then the last part is saying there is Cl minus in this solution, but Cl minus's ability to force H to hang out with it is almost zero. So what it's saying is the reaction Cl minus plus H goes to HCl. That doesn't really happen. Like we can make it, but in water, when it's dissociated, this does not have the ability to grab an H and become protonated. It resists protonization. So if we had this equation right here, Cl minus plus H goes to HCl, we would not do this. There'd be zero, almost zero products. So they would stay broken apart. That's all a strong acid does. It stays broken apart.
So if you have a strong base and it becomes an acid, the acid's going to be really weak. Strong base.
The conjugate acid is extremely weak. Strong bases have basically zero, that's a stupid word to use, ability to come back the other direction, basically. Okay. Weak acids only dissociate partly in water. Their conjugate bases are weak bases, meaning they go one way. If it's a strong anything, it goes towards the products. If it's weak, it kind of goes both ways. So a weak acid like vinegar, you're going to have HC2H3O2, some of that. You're going to have some H plus. I don't know, I just dropped it because I didn't want to use it. And some C2H3O2, but the concentration of this is really big and the concentrations of these are really small. It's almost all predominantly molecular, meaning it doesn't dissociate. So this is why we can eat vinegar when it's sour, but it doesn't kill us. But if we ate hydrochloric acid, we'd be in a lot of trouble. Right. And then that H plus would go down your throat into your belly and you would just be wrecked.
You also wouldn't be able to turn it back.
All right. Okay. So this is in the book. I'm sure you'll love looking at it. Strong acids, negligible conjugate bases. Strong bases, negligible conjugate acids. So this is why if I add table salt, NaCl, if I add that in here, I have Na plus and I have Cl minus, the pH of salt water and the pH of neutral water are the same. Because Na is a weak conjugate acid, base, it cannot grab an OH. It dissociates completely. So that doesn't happen. And Cl can't grab an H. That doesn't happen. Now, if I added HCl to water, I'd have a pH of 1 and pure water be a pH of 7. And that's because these two can. All right, so it's a little tricky, but if I add these weak conjugates, the pH of the solution does not change. And we'll learn about that. And we'll just wrap it up right there. Okay, tomorrow's test, I think for half of you, it will take 20 minutes. The other half, it'll take the whole hour. Where? Oh, I did that myself? Oh, that one didn't make one? All right. I better stop before this gets super loud.